in a physically sensible spacetime, in a sufficiently small region, two points are connected by a geodesic that's unique if you want it to be inside that region. I didn't want to give the technical definition of strong causality because, as I said, when I wrote my lecture notes a couple of years ago, I found that frustrating and unenlightening to explain. And I decided to just offer this property as a stand-in for strong causality. So every point is supposed to have a small neighborhood with that property. Sorry. What I just said was a mixture of two things, unfortunately, so I got it a little bit scrambled. But I'm not going to try to unscramble it right now, because I think you got the idea right.
Why will strong causality imply that if the converse is also true?
Sorry. No. There are two, sorry. Well, the question kind of forces me to unscramble myself. If we stipulate that the geodesic is in the neighborhood, then the existence of a small neighborhood with this property is a general theorem about spacetimes. This is what we call a local Minkowski neighborhood. Strong causality implies the following, that if P is sufficiently close to Q along a time-like path, then there's no time-like path that goes outside the neighborhood that would get back there. So it prevents the existence of a time-like path that does something like that. I haven't defined it precisely, and I don't really want to. If you want to know exactly the conditions about strong causality, look at either Wold's book or else my lecture notes. It's what I was trying to keep away from in these lectures.
I have a question.
Yes.
So in last lecture we talked about that in any manifold, the inextendable curves from any point would be compact under a certain metric.
Yes.
But what if, for example, one of the curve goes into a singularity, and that is the limit of the sequence?
The limit of the sequence is allowed to approach a singularity. A curve that ends at a singularity is inextendable. It can't go farther.
Yes, but I would imagine any curve that is close to that curve would miss that singularity and goes further.
Well, if you look at the proof, you'll see that the proof works fine in that situation. Yes. What it will tell you is that, first of all, the curve that ends at the singularity had infinite length because we picked a complete Lorentz signature metric.
Yes.
And then you have all these curves. As they get closer and closer, the arc length gets longer and longer as you get near that point. And they simply do converge to this one. So remember, you have to look carefully. Well, in a way, the first homework problem is not exactly aimed at your question, but it's aimed at helping you understand the fine point of exactly what we proved. So what we did was we parameterized the curves by arc length in a complete metric. And those parameterized curves have a limit. And that will happen just because the parameter is going to infinity. Well, the farther you get this way, the bigger is the parameter over here. It's possible that you would find the statement dissatisfying from some points of view, but for the application which we actually want, which will be what we'll discuss in the first 5 minutes when we get started today, what we proved was was useful.
Can I say this compactness is only under this specific metric, or it's universal?
it's the question is more convergence. So in what sense does a sequence of curves converge? Here they're parameterized curves. And the statement was that what we actually proved was that they converge as parameterized curves, which is different from proving a sequence of curves converges up to reparameterization. We actually proved that they converge as parameterized curves. As parameterized curves, this tail gets lost in the limit because the parameter goes to infinity first. So since what we proved involved the parameterization, you're correct that it involved the complete metric. Well, we're almost all here, but maybe we have time for one more question from last week before we get started. So, okay, so maybe we'll get started today. One thing I'll remark is that there is some homework. You can find it at my website under Physics 539. So the last thing last time so on any manifold M, first we observed that on any manifold M we can pick a complete Euclidean metric. And then we considered a sequence of inextensible curves that start at a point Q. And we parameterized them by arc length, and we showed that any sequence of inextensible curves has a limit. These are inextensible curves that we parameterized by arc length. In some complete Euclidean metric. So, as I remarked a moment ago, before some of you came in answering a question, this was a statement about parameterized curves. So, as parameterized curves, there's a limit. It's not a limit up to reparameterization. Anyway, there was no mention of a Lorentz signature here. Or of causality. However, now we're going to apply the statement to a Lorentz signature manifold. So now, we assume M has Lorentz signature. So, in other words, M has a Lorentz signature metric that we're actually interested in. We picked an auxiliary Euclidean metric that we weren't interested in to make that proof. But now we're going to apply the statement to learn something in the Lorentz signature metric that we do care about. So we assume that M has Lorentz signature, and we assume that the gammas are all causal curves. So causality, we recall, is an inequality. Let me write it without the square root. So minus g mu nu dx mu ds dx nu ds is equal to or greater than 0 for all the gamma n's and for all s. Since it's an inequality, it will remain true in a limit. So therefore, the limiting curve gamma star is causal. So this argument shows that in general, in any Lorentz signature spacetime, not necessarily globally hyperbolic, a sequence of causal curves has a limit in this sense. This sense is a little tricky, and the first homework problem is aimed at helping you understand a little bit better some of the trickiness. Yes?
Does it mean that it has a subsequence which has a limit?
Sorry, you're right. Any sequence has a limit point, which means it has a convergent subsequence. Thank you. Sorry, I forgot that I wasn't planning to wear a mask when I speak, but I do recommend masks for the rest of you. I see most of you have them. Now, okay, this is, okay. Now there's one more fact, which is that the gammas all had infinite arc length, because any inextendable curve in a complete Riemannian manifold is infinite arc length. They have infinite Euclidean arc length. And gamma star was the limit of a subsequence of the gammas as parametrized curves, not just as abstract curves. So it also has infinite arc length. Infinite Euclidean arc length again. And therefore it's inextendable. A curve that's infinitely long in the Euclidean metric is certainly inextendable. So we've learned that in a Lorentz signature spacetime, we learned that a sequence of inextendable causal curves has a limit point. In other words, it has a convergent subsequence. That's still a little bit abstract. Now we're going to get something useful by assuming that our spacetime is globally hyperbolic. As we discussed last time, for M to be globally hyperbolic means, with Cauchy hypersurface S, means that every inextendable curve meets S. Yes?
In the previous group, where did you use the fact that they were causal curves?
I wanted to deduce that the limiting curve is causal. That means it obeys a certain inequality. Well, that won't be true in general, but if each of the gamma i's obeys that inequality, then any limit will obey the same inequality. So the limit curve is causal if all the curves that are having a limit is causal. Otherwise, it's certainly untrue. If you have a bunch of space-like curves, they can have a space-like limit, for example. So globally hyperbolic means that, for example, if you have a point Q to the past of S, then any inextendable curve to the future from Q, any inextendable causal curve passes through S on its way. That was part of the definition of globally hyperbolic. Now, what we're trying to do, remember that curly CQS is the space of causal curves from Q to S. We wanted to show that it's compact. Which means that any limit has a convergent subsequence. So we consider our sequence of causal curves from Q. Well, what do we know? Well, on the last blackboard, we asserted that it will have a subsequence that converges to an inextendable causal curve. So here's the limit. Gamma star is causal and inextendable. Having those properties, it must meet S by the definition of globally hyperbolic. So we found that if we have a sequence of causal curves from Q to S, it has a subsequence that converges to a causal curve from Q to S. In other words, we've shown that the causal curves from Q to S are compact. Any questions about that? Historically, that was the original definition of globally hyperbolic by Leray in the 1950s. But it's a slightly opaque definition to most people. The definition we used, has more to do with the idea that initial data can be specified on a Cauchy hypersurface. So the two definitions are equivalent, but we started with the one that's, I think, is better motivated physically, and deduced this one. Now, there's a variant of this statement. We can have a point P and a point Q in its future and consider causal curves from P to Q. This is also compact. I'll just give a quick proof, assume that, so I'm going to assume in here that Q and P are to the past of S. The argument will obviously be the same if they're both to the future of S. If one is to the past and one is to the future, I actually left it as a rather easy, hopefully rather easy homework problem that you'll find up there. But I won't explain it in the lecture. So since P is to the past of S, we can pick a causal path, gamma 0, let's say, from P to S. And then if we have a sequence, gamma 1, gamma 2, and so on, so we have these paths gamma I from Q to P, and we have a fixed path gamma naught from P to S. So we can take their convolution, gamma naught composed with gamma I, from Q to S. And we've already proved that that sequence of causal paths from Q to S has a convergent subsequence, and that convergent subsequence will be the convolution of the path from Q to P and this fixed path from P to S. So once we know that the space of causal paths from a fixed point to S is compact, it's an easy corollary that the same is true for paths from a fixed point to some other fixed point. I stated the argument for both points to the past or equivalently both to the future of S. I think if you think about it a little bit, you'll see that a similar argument holds in case one is to the past and one is to the future. But I'll leave you to think about that. So what we've shown has got a lot of nice corollaries. So one obvious one is that we can take the intersection of the future of Q so we take the causal future of Q, all the points that can be reached from Q by future going causal paths. And we also take the causal past of S. I always allow trivial, I consider a path that consists of only one point to be a causal path. Otherwise, one has to state too many exceptions. So Q itself is contained in its own causal future because it can be reached by the trivial path from Q to itself. Likewise, S is in its causal past. So then we look at J plus of Q intersect J minus of S, which are points we can reach from Q by a causal path. Well, so in the example, it would be something like this set. So I claim that this is compact as an easy corollary of what we've just proved. How do we know it's compact? Well, suppose we have saying it's compact means if we take any sequence of points, R1, R2, and so on, in that set, it has a limiting subsequence. So take any point R in this region. It's to the future of Q by definition, so we can reach it from Q by a future going causal path. It's the past of S, so we can continue on to S. And now if we have a sequence of such points, so that was R1, here's R2. Do the same for R2. We have a sequence of points that can be reached by these causal paths from Q to S. Well, if the R's didn't have a limit because there was a hole here, a point missing, then this sequence of curves couldn't have a limit. So in other words, the sequence of curves has a convergent subsequence. On each of them is compact, each of them has one of these points Ri. The limit of the Ri's will give the point we want on the limit curve. So we learned that nothing can be missing, that the future of Q intersected with the past of S has to be compact. The same argument would apply if we have, let's remember where we were sort of halfway through Tuesday's lecture. We discussed the fact that, we had discussed some implications of the fact that causal diamonds in Minkowski space are compact. And we wanted a useful criterion that would make causal diamonds compact in general. And then we looked at some examples where causal diamonds were not compact. So we saw that a non-trivial condition was needed. And then I started explaining global hyperbolicity, which I said was a condition that would make causal diamonds compact. And now we learn that because, you see, J plus of Q intersect J minus of P, which is the causal diamonds. I guess we called it dPQ, is compact by the same kind of argument I just gave. If there was a sequence of points in the causal diamond that had no convergent subsequence, because it intuitively approaches a hole, then a sequence of causal paths through those points would also have no convergent subsequence. So we've learned that global hyperbolicity does the job that I said it was going to do when we introduced it, of making causal diamonds compact. Okay. Global hyperbolicity has a lot of other corollaries. I'm going to first state one that's a little bit deep, and then we'll discuss some more elementary ones. So one easy corollary. So if Q is to the past of a point P or of a Cauchy hypersurface S, there always exists a geodesic, a time-like geodesic from Q to P or Q to S of maximum proper time. This follows, we discussed this first in the context of Minkowski space Tuesday, and then we decided it would be true in general if the causal diamonds are compact. The idea was just that you consider a sequence of causal paths with increasing proper times. And that sequence must have a convergent subsequence because of compactness. And the convergent subsequence maximizes the proper time of any causal path that satisfies the conditions from Q to P or from Q to S. So it's automatically a time-like geodesic. I see slightly puzzled faces, so I'm going to go over the argument in more detail, although it'll be similar to what we said Tuesday. First, we need to know that the proper time has an upper bound for a causal path from Q to P or from Q to S. It has an upper bound because if there were a sequence of causal paths where the proper time was going to infinity, then the same would be true for any subsequence, and therefore such a subsequence couldn't converge. So therefore there is an upper bound on the proper time of any causal path from Q to P or from Q to S. Now consider a sequence of causal curves where the proper time of that sequence is converging to the least upper bound. There's an upper bound, so there's a least upper bound. We then look at a sequence that converges to the least upper bound in proper time. It has a convergent subsequence, and the convergent subsequence will be a path that maximizes the proper time. On the other hand, by calculus, we know that a path that maximizes or even extremizes the proper time is a geodesic. So thereby we deduce that there's a geodesic of maximum proper time. Maximum proper time not just among geodesics, but among all possible causal paths. So that's true for a path between two given points or between a given point and a Cauchy hypersurface in a globally hyperbolic spacetime. And after a little while, I'm not sure if it will be today or Tuesday, you'll start to see how that's useful in proving non-trivial statements in general relativity. Now, there are a few easier corollaries of global hyperbolicity that I also want to explain. So one is that a globally hyperbolic spacetime has no closed well, first it has no closed time-like curve. Sorry. Yeah, I think I'll just say no closed causal curve. So, why is that true? Well, remember, every inextendable causal curve meets S. If you had a closed causal curve that doesn't meet S, you could go around that curve infinitely many times. That would be an inextendable causal curve that never meets S. On the other hand, it might meet S. That means it starts to the past of S and then goes to the future of S, and then comes back to the past. So that would mean that there's a point, P, which is both to the past and the future of S along that curve. But part of the definition of global hyperbolicity is that there's no point both to the past and the future of S. I realized after Tuesday that I hadn't explained the motivation for that part of the definition. So the main motivation, so in introducing a globally hyperbolic spacetime, we had a condition that ensured that every signal could be considered to have originated on S, so that it's possible to formulate initial data on S. But we also want S to have the property that initial data can be freely specified on S. So, you see, suppose that we had a point that was to both the past and future of S. Here's part of S. Here's a point that's to the future of S. But then it's also to the past of S. So here's a different part of S. Then causal signals would be reaching S from S to itself. And we wouldn't want to specify initial data here independently of what there was here. So if we allowed a point to be both to the past and future of S, S wouldn't correspond to our intuitive idea of an initial value surface, and it wouldn't have the properties we usually want to claim that initial value surface has. In answer to one of the questions last time, I did give an example of a perfectly good spacetime with an S that was good in all respects, except that there are points to both its past and the future. So the spacetime was a cylinder where space, this was in 2 dimensions for simplicity, space is taken to be a circle, time goes from minus infinity to infinity, going upward in the picture. But then we pick an S that wraps around in the way I've indicated. So every point here is both to the past and future of S. And you certainly wouldn't want to try to specify initial data on such an S, because that would be highly redundant and overdetermined. I mean, for generic initial data on S, there would be no solution at all. Now, so there's no closed causal curve in a globally hyperbolic spacetime. There's also a stronger statement, but harder to prove. If you're interested in a proof, you can look at Wald's book or at Appendix D of my lecture notes. You can't come arbitrarily close to having a closed causal curve in a globally hyperbolic spacetime. It's strongly causal. We're not going to use that, and I'm not going to prove it. Let's see if there's more I wanted to say. Oh yes, I want to discuss the topology of a globally hyperbolic spacetime. So since I'm changing the subject slightly, any questions on this? So M is our globally hyperbolic spacetime with Cauchy hypersurface that I usually call S. So it has a Lorentz metric that we're interested in. But as is often the case, it's convenient to study it by introducing an auxiliary and rather arbitrary Euclidean signature metric. And last time we proved that we can assume this metric is complete. Complete means that inextensible curves have infinite length. And we proved that by first proving that there was some Riemannian metric on M, and then proving we could Weyl rescale it to make it complete. We just Weyl rescaled it by a factor which intuitively blows up as you approach infinity in M. I won't repeat today the exact construction. For those who weren't here today, Tuesday, you can find it in Appendix C of my lecture notes. So we do that again. We again pick this complete Lorentz signature, complete Euclidean signature metric. Now, at a point P in S, we can diagonalize, well, we can pick coordinates so that H mu nu is just the Kronecker delta. In other words, we pick locally Euclidean coordinates for the Euclidean signature metric. Then G mu nu is symmetric, and any symmetric matrix can be diagonalized by an orthogonal transformation. So we make an orthogonal transformation in the Euclidean signature metric to diagonalize G mu nu. Then when we diagonalize it, it has one negative eigenvalue and a bunch of positive eigenvalues. The negative eigenvalue, of course, points in a direction that has Lorentz signature in the Lorentz signature metric. And we can pick a vector in that direction which is time-like directed, future-directed, sorry, rather. Any vector in that direction is time-like, but we pick a future-directed time-like vector that's an eigenvector of G mu nu with negative eigenvalue. And then we can moreover make it a unit vector in the Euclidean metric. So what we get from this is a future-directed time-like vector field V that's a unit vector in the Euclidean metric. Just to go over it again, at a point we pick local Euclidean coordinates where the Euclidean metric is the Kronecker delta, the standard Euclidean metric. That's invariant under an orthogonal transformation. We use the orthogonal group to diagonalize the Lorentz signature metric, whereupon it has a negative eigenvector, and the negative eigenvector gives you a time-like direction. We pick a vector in that direction, which is unit length in the Euclidean metric. That would fix it up to sign, and we fix the sign by saying we want it to be time-like in the Lorentz signature metric. So by an interplay of the two metrics, we've picked a vector field, V, which is time-like, and also it's a unit vector for the Euclidean metric. Now, having found a vector field, you can solve an equation, the equation for what are called integral curves of that vector field. The equation just says that there's a parameter s that will parameterize a curve. At each value of s, dx ds is the vector field. So you go in the v direction. And as long as you're on a smooth manifold and v is a smooth vector field, you can always solve this equation. The only thing that might happen in general is that you might not be able to solve it in general for all values of s. You might reach a singularity, or you might reach the end of the manifold, whatever that means. For example, with no completeness on the Euclidean metric, you might reach infinity in the Euclidean metric after some evolution in S. Here, however, since I normalize V to be a unit vector in the Euclidean metric, that means that S is just an arc length parameter along the integral curves. And since we chose the Euclidean metric to be complete, every curve can be extended up to infinite arc length. So in this case, we can solve for all s between infinity and minus infinity. That's true because we went to the trouble of getting a unit vector field in the Euclidean metric, so our curve is automatically parameterized by arc length. And because the Euclidean metric is complete, a curve parameterized by arc length and also inextendable has infinite arc length in both directions. So in this case, inextendable simply means that we can't solve it any farther. Yes?
You define the vector field only on the surface S, right? Because you started with a point on the surface.
No, I started with any point in M.
Oh, you said any point.
Oh, sorry, that was a slip. Thank you. We didn't make any use of the existence of S so far. We're about to.
But just to be clear, right, you cannot create these locally flat coordinate systems simultaneously, but you can still use this as like a description for defining
I didn't pick locally flat coordinates.
You didn't?
No, I didn't pick coordinates. I picked coordinates to make this true at one point P of interest.
Yeah.
So it wasn't
That's simultaneously, but you still use it.
for each P.
Yeah.
For each P, picking coordinates was just a way to make the description less abstract.
Okay.
I could have said, in the tangent space of every P, there's an orthogonal group that leaves invariant the Euclidean metric at that point. And then I would use that group, and I would make the argument without having ever mentioned coordinates.
Yeah.
I was trying to make it more concrete, but you're right that in making it more concrete, I introduced a separate discussion of a coordinate system separately at each point P that we want.
I see, thanks.
Any other questions?
I have a question.
Yes?
Is there some kind of argument that implies that this will be smooth? Something like in the tangent bundle, things are...
Well, informally, all the steps in this discussion are manifestly smooth. Assuming the input is smooth, the output is also smooth. I'm probably not the right one to give you the precise theorems about ODEs to make that true. So I will refrain. However, one frequently needs intuition about points like that, and sometimes points that are more subtle than that. Many similar questions to that one will arise. And we will not worry about precise mathematical statements. Any other questions? Well, one thing about this is that I didn't tell you, see, this equation is invariant under shifting S by constant, so we haven't quite determined it. Well, okay. Okay. Now, the integral curves, what properties do they have? Well, they're time-like, because V was a time-like vector field, and they're inextendable because they have infinite Euclidean arc length in both directions. So they meet S in a unique point. So each gamma, each one of these gamma has a property that its intersection with S is a unique point P. We could call it gamma P. Gamma P is a point, or maybe I should call it P gamma. Gamma P or P gamma is a point in S. Well, in S intersect gamma, but there's a unique such point. So the picture looks something like this. Here's one gamma, here's another gamma, here's a third gamma. Now, the equation for the integral curve would be invariant under adding a constant to S. So we can add a constant to S, and we can require that S is 0 on S for all gamma. In other words, I didn't really uniquely determine what I meant by the parameter S for you, because it was only well-defined up to a constant. But since each integral curve is meeting the hypersurface S in one point, I can fix the specification of the integral curves, the parameterization of the integral curves, by saying that the parameter little s vanishes on big S. At this point, you can see that we've determined the topology of M, namely, M is S times R, where R is parameterized by little s. In other words, we can identify a point in space-time by, if you have a point P in space-time, it's associated to a unique point, well, it's contained in a unique gamma, and then it's associated to a unique point gamma P in S, and then it has, to complete specifying where it is, there's a, I think I need to write bigger so you can see, but I also need to distinguish big S from little s. Okay. So is it clear from what I've said that we've learned that the topology of a hyperbolic 3 manifold is simply a product of the initial value surface times R, where informally you can think of as R as parameterizing the time.
There's never a twist?
Well, the question was, is there ever a twist? There's never a topology more complicated than this, because we've proved that this is the topology of a globally hyperbolic spacetime. So that means that that's why topologists like Euclidean signature. Sorry. The global hyperbolicity was crucial here. If we didn't insist on global hyperbolicity, you can have a lot of complicated topologies in Lorentz signature. But interestingly, you would find that not all topologies allow a Lorentz signature metric, even if you don't care about global hyperbolicity.
But does this still allow the topology of S to change over time?
The topology, no, well, okay. The question was, can the topology of S change over time? Let me reformulate that question. Do all possible S's have the same topology? Well, suppose we have two S's, S and S prime. I proved that M was S times R, but the same argument would have proved that M was S prime times R. So therefore, S times R is isomorphic to S prime times R. Now, as a general statement in topology, topologists will actually tell you that that does not imply that S and S prime are equivalent as smooth manifolds. But in this case, they are, because here's some other S prime, and I want to prove it's equivalent to S. Well, I just map a point in S prime to the point in S that's on the same integral curve. And that map is obviously smooth and invertible. So therefore, S and S prime are topologically the same. So I think that's a precise statement of the fact that S topologically can't change in time. But there is a stronger statement that's in the same spirit. I think I need to define an achronal set. A set C. So a set C in spacetime is achronal if there is no time-like curve from C to itself. Now, suppose we have an achronal set C. Achronal means, in particular, that an integral curve can't intersect C twice, because the integral curves are time-like, and if an integral curve intersects C twice, it's a time-like curve from C to itself. So each integral curve intersects C at most once. So if you pick a point in C, it's on some integral curve, which intersects C only at that point, and then we can map C to the point in S, which is on the same integral curve. Now, contrary to the example I just gave in answering the question of whether S can change in time, here this map is not invertible. It's only a one-way continuous map. But we get a continuous map. So the map phi, which takes C to S, by mapping a P to gamma P, phi is an embedding of C in S. So therefore, every achronal set is equivalent topologically to part of a Cauchy hypersurface. We prove that the Cauchy hypersurfaces all have the same topology, so in that statement you can pick any Cauchy hypersurface. So this will ultimately be a key step in the proof of Penrose's singularity theorem, which we'll get to in about 3 lectures, I would say. Maybe a week from today or a week from Tuesday. Now, yes?
In this discussion, do you assume if S has a boundary or not, it's compact or non-compact?
Manifolds, by definition, don't have boundaries. So first of all, M is spacetime. Spacetime we defined as a Lorentz signature manifold. In a manifold, every point has a neighborhood isomorphic to an open set in Euclidean space. So by definition, a manifold, and in particular M, does not have a boundary. S was a hypersurface. a hypersurface in a manifold is also a manifold. So S has no boundary. However, no assumption is made about compactness. We never have compactness because at least compactness fails in the time direction. We prove that a globally hyperbolic spacetime is S times R, so it's always non-compact. But we might or might not have compactness in the spatial direction. So S could be, roughly speaking, S could be more or less anything. It's not literally true that S can be anything. You can show that there are manifolds in which you can't satisfy the Einstein constraint equations. So there end up being topological restrictions. So, I want to mention a slight refinement of this last statement. If C is an achronal manifold, an example would be C equals S. Sorry. I have to, not just manifold, hypersurface. So hypersurface is a codimension 1 manifold. I was about to say something true for hypersurfaces, but not in general for manifolds of higher codimension. There is no causal curve from C to C. So achronal said that there's no time-like curve. But if C is actually a hypersurface, there's automatically no causal curve. Well, the difference is just I need to prove that there's no light-like curve. So imagine there is. So we have some picture like this. And gamma is light-like. So we're given that gamma can't be time-like because C is achronal. We want to prove that gamma can't be light-like. Well, you see, C is a hypersurface and it's also achronal. So that means that C is space-like. Sorry. I started worrying whether C could be null, so to avoid it, let me just specify that C is a space-like hypersurface, because that's the case we're actually going to be interested in. On a space-like hypersurface, you could move the initial, see, gamma is pulling in some direction. Gamma is a null vector, so it goes forward in time, but in some direction in space. Since C is a hypersurface, you could have moved the starting point of gamma along C in the direction of gamma a little bit, while we're getting another point on C that's a little bit closer. Then if you start a little bit closer, you're trying to travel no faster than light, but you're going a little bit less distance than gamma did. So then you could modify the curve a little bit to be everywhere time-like. In other words, a light ray travels a certain distance in a certain time, but if you reduce the distance, you could have traveled there slower than light. So C being a space-like hypersurface means we could have moved the starting point in a way that would have reduced the distance a little bit, and therefore we could have reached the same endpoint with a path that's time-like rather than null. So although in general achronal says there's no time-like curve, for space-like hypersurfaces, it implies that there's no causal curve. So an important example is the Cauchy hypersurface itself. There's no causal curve from S to itself. I think we knew that already for other reasons, but this explanation would give, this would be one explanation. So there's a special case of this that Penrose used, which is that if C, so that if S is non-compact, and C is an achronal hypersurface, then C is not compact. So this statement seems a little bit bizarre. It'll be much better motivated when we're getting to Penrose's proof. Therefore, I'm going to repeat the explanation of this point when we actually get to Penrose. But to just tell you the idea now, well, this argument showed that since C is achronal, it's topologically equivalent to part of S. But a non-compact hypersurface, there's no part of it which is a compact submanifold. The only way to get a submanifold of a manifold of the same dimension in a manifold is to throw away part of it. But throwing away part of a non-compact manifold will never make it a compact manifold. All you can do is make more holes. So therefore, if we know that C is achronal and compact, well, it's impossible for C to be non-empty, achronal, and compact, and a compact manifold. So I'll go over that again when we need it, when we're proving Penrose's theorem. Okay, now we're going to start a new topic, so maybe it's a good time again to stop for questions. Yes?
With these last few results, were we assuming M was globally hyperbolic?
Yes.
Yes.
I assumed M was globally hyperbolic because that went into saying that an achronal set C is topologically equivalent to part of S. And if S is a non-compact manifold, no part of S is a compact hypersurface, which would be a manifold of the same dimension. And therefore, it's impossible for C to be an achronal compact hypersurface.
And so why did we need to say that C was, in the previous part, that C was both achronal and spacelike? If you have a space...
We didn't need it for this, I don't think.
Okay.
But I wanted to say that C, there can be no causal curve from C to itself. Not just... achronal says there's no time-like curve. For other applications, I don't remember if we need it for Penrose's theorem. I think not, but it's useful to know that there can't be also a causal curve from C to itself. But that depended, see, had C been null, that would have been less obvious. It might be true anyway, but it's less obvious. I use the fact that you can move the initial point in any spatial direction, thereby shortening a path. Had C been null, I don't want to make a quick claim about whether we could modify the argument or not. But it would have been less obvious. Any other questions?
But if, sorry, so if we just said spacelike and not achronal,
Yeah.
like, is a spacelike hypersurface in globally hyperbolic spacetime automatically?
No, there's this example I keep giving of one that isn't. Okay, I gave this example to illustrate something else, but the question is, what's a space-like hypersurface in a globally hyperbolic spacetime that's not achronal? This one, which fails to be a Cauchy hypersurface, also isn't achronal, right?
Oh, okay, but this is still globally hyperbolic.
The spacetime is globally hyperbolic. S is not a Cauchy hypersurface. A Cauchy hypersurface is achronal, but just a generic space-like hypersurface might not be. Any more questions? Okay, now we're then starting a different topic. And the goal is going to be to navigate toward the simplest singularity theorem, which is Hawking's theorem about the Big Bang. The most important singularity theorem, and also historically the first, was by Penrose. But it takes more ideas to explain it. I thought it would be more fun if we had a payoff sooner. So we can get to Hawking's theorem on Tuesday. I think not today. But we wouldn't have been able to get to Penrose's theorem on Tuesday. So just so that we can do something fun along the way, with only some of the ideas, we're going to navigate toward Hawking's theorem first. So we're going to ask this question. We're going to start in Riemannian geometry. So is a geodesic the shortest path between 2 points? Well, so here's a point Q and here's a geodesic. If you have a point P which is sufficiently close to Q, so P is sufficiently close to Q along gamma, then gamma is length minimizing. But if you continue a geodesic, you're typically stopping length minimizing if you continue it too far. For example, let's suppose that we're working on a sphere. And Q, okay, we could take Q to be the south pole. And now a geodesic is a great circle, and until it'll eventually reach the North Pole. Until you reach the North Pole, your geodesic will be the shortest path from P to Q. But a little thought will show you that once you've passed the North Pole, that's not true. Over here, the same gamma, so gamma from Q to P is minimal. But gamma from Q to P prime is not minimal. Because it's obvious that if you really wanted to get over here, instead of going over the North Pole, you could have saved some length by going around the other way. Now, there's a very useful, sufficient criterion to know that a path is not minimal. You see, let's look at this example. The path from Q to P was unique when it was minimal as long as P was closer than the North Pole. But once you reach the North Pole, let's call it Pn maybe for North Pole, the path to the North Pole was not unique. There were a lot of equivalent paths that would have reached the North Pole in the same length. So it helps to straighten out the picture. This is a picture on a curved surface, but of course a geodesic is intrinsically flat, and the immediate neighborhood of a geodesic is also flat. You have to go to second order near a geodesic to learn that to see the Riemann tensor and know that the manifold is curved. So I'm just going to draw our geodesic as a straight line. Well, I didn't draw it very straight, but and then here's meant to be the North Pole, and here we've continued past there. But we know that when we got to the North Pole, there was another geodesic that was just as good. Now, of course, this picture I can't really draw on a flat blackboard. Well, I couldn't draw it properly on a flat blackboard because it wouldn't be true on a flat blackboard that there are two geodesics from Q to Pn. On the sphere, there are. But we're imagining it's true. And if you zoom in on a small neighborhood of Pn, what's happening is just that so here's gamma prime. There's a different path to the same point Pn. It somehow reaches Q in the same length. I'm drawing dotted lines because I can't draw the picture realistically on a flat blackboard. You see, as soon as you have this picture, it's automatically true that gamma can't be length minimizing, because you can reduce the length as follows. By hypothesis, there's a nearby gamma prime that would not increase the length along part of the journey, the part from Q to Pn. So I first replace gamma by gamma prime. But now I have a path that isn't a geodesic because at Pn it doesn't satisfy the geodesic equation, and it actually takes a bend. So now I can smooth out the bend. Now I've reduced the length of the path. So, you see, what it means in the sphere is this. We have the geodesic that goes past the North Pole. It's not optimal. We could do better by, well, we could do equally well by taking a different path as far as the North Pole and then retracing our steps as before. But since there's a kink up near the North Pole, we could improve it by rounding things out. And you see, if you round things out, you're beginning to deform the direction in what is actually, you're beginning to deform toward what actually is the shortest path from Q to P. To P prime. So, this point where the different geodesics meet, well, I like the phrase focal point, but a lot of people call it a conjugate point. If different geodesics from Q focus at the same point Pn, then any one of them when continued past Pn is not length minimizing. Because whichever one you continue with past Pn, you could have done better by taking the other one and then rounding out the bend. So a geodesic is not length minimizing past a focal point. This is a sufficient condition for a geodesic to not be length minimizing. It's not a necessary condition. A geodesic could stop being length minimizing because when you go too far, there happens to be a completely different way to get there faster, even though it didn't happen through a focal point. What I've described is similar to a second-order phase transition in thermodynamics, where you can see locally that your path stopped being length minimizing. But there could be the analog of a first-order phase transition, where locally the path looks perfectly good, but actually if you go too far, there was some completely different way of getting there faster. For example, instead of a sphere, we could have considered a circle. So a geodesic that goes more than halfway around the circle is not length minimizing because that was the wrong way to go. It would be better to go back the other way. But in this case, there's no focusing of different geodesics that would tell us that. So this is you could make more sophisticated examples, but this is a trivial example where a geodesic stops being length minimizing even though there's no focal point. But anyway, the failure to be length minimizing because of a focal point is crucial in all kinds of applications in general relativity. More exactly, the analog of that for causal curves. So we'll be focusing, if you'll excuse the expression, on focus points, focal points. Sorry. Okay. Now, I want to be more precise about what we mean by a focal point. In the case of a two-sphere, well, I drew a two-sphere, but this could have been an n-sphere. In the case of a sphere, all geodesics from the South Pole focus at the North Pole. But for this argument, we didn't need that fact. For this argument, we only needed the fact that there's some nearby geodesic that would focus to the same point. And we don't even need that. We need only infinitesimal focusing. Meaning that, so here's a geodesic from Q to some point that we claim as the focal point. To decide if it's a focal point, we look at the equation for a first-order deviation of a geodesic. And so if gamma prime exists to first order, that means that the geodesic equation has a zero mode that vanishes both at Q and also at this focal point. That's really the definition of a focal point. That's enough for this argument. Why is that the case? Well, let's displace this geodesic by an amount epsilon. First, suppose we don't have a geodesic. Suppose we don't have a focal point. Every geodesic is an extremum of the length. So, always, the length of gamma prime minus the length of gamma is of order epsilon squared if gamma is geodesic. Because a geodesic is an extremum of the length, so changing the curve to first order won't change the length. It will change in second order. A zero mode means that if we pick gamma prime correctly, L gamma prime minus L gamma is of order epsilon cubed. Exact focusing of a geodesic would mean that L gamma prime equals L gamma. But I want to consider the case that infinitesimally we can deform gamma to a nearby geodesic that connects these 2 points, but not exactly. If it's only true to first order, that means we can't assume that L gamma prime minus L gamma is 0, but we can assume it's of order epsilon cubed. With a coefficient that's positive, assuming that, in the case we're interested in. The case we're interested in is the case that gamma was length minimizing, at least up to the focal point. So that tells us that the coefficient of epsilon cubed can't be negative, since if it was, well, length minimizing behavior already failed before. So a zero mode means that when we displace the gamma slightly by an amount of order epsilon, we increase the length by an amount of order epsilon cubed. Now, we also create a kink here, and the kink angle is epsilon, is of order epsilon. And now we round out this. We have a kink with a kink angle of order epsilon, and that reduces the length by epsilon squared. So if we didn't have a zero mode, we wouldn't necessarily win, because displacing the geodesic in the bulk would add epsilon squared to the length, and rounding out the kink would reduce it by epsilon squared. And in general, we wouldn't win. We might not. Geodesics to a given point might or might not be length minimizing. When we have a zero mode, the displacement only increased the length by epsilon cubed, and the round-off improvement was epsilon squared. So we're guaranteed to win. So that shows us that when we continue past a focal point, where a focal point is just defined in terms of a first-order deformation, we reduce the length. There was a question I saw.
Yeah, why is the angle at order epsilon?
Well, we're keeping this length fixed by trigonometry. We have a triangle whose height is epsilon and its base is of order 1, so the angle is of order epsilon. I mean, you hold a rope, you're holding a rope, and I displace it vertically by an amount of order epsilon. That'll change the angle by an amount of order epsilon. You could worry it will change it by less, but, well, the geodesic equation will tell you that you can't change it by less. In other words, if this is a zero mode, it obeyed a linear equation, which was second order. You specify the initial point. Well, any deviation of the geodesic changes the angle. So the zero mode has a shift in angle. Then we add the zero mode with the coefficient of epsilon, so the angle changes by an amount of order epsilon. But what I'm saying should be obvious. There's no technicalities. You had a rope and you displaced it by an amount of order epsilon, so the angle changes by epsilon. Any other questions?
So in a geodesically complete space, the infinite would be sort of a focal point, right? Or like all geodesics would, but it's not in the space, so we're not concerned.
Well, we don't. Here we are interested in geodesics between finite points. But see, the trouble with your question is that infinity, we would have to discuss what's meant by infinity. Infinity, I mean, the different directions a geodesic could go to infinity. Discussing infinity would become complicated. Any other questions? Now, instead of considering a geodesic between that has a specified initial point, we could consider a geodesic that starts on some specified initial set. And the easiest case is that W is a codimension 1 submanifold. For example, when we get to Lorentz signature, W might be a Cauchy hypersurface. But in general, let W be any hypersurface. Then we look at a path from W to some point M. And we're interested in minimizing the length. Well, an extremum of length is, of course, a geodesic that's orthogonal to M, to W, I tried to say. So let's just discuss, so even to get an extremum, let alone a minimum, we will want an orthogonal geodesic. So let's discuss an orthogonal geodesic. So if gamma is an orthogonal geodesic, then a point on gamma that's sufficiently close to W will have the property that gamma minimizes the length between W and that point. But again, if we go too far, that will fail. In the example of the two-sphere, we could take W to be the equator. Then the orthogonal geodesics to the equator all converge at the North Pole. They're length minimizing before you get to the North Pole, but when continued past the North Pole, they fail to be length minimizing for the same reason as before. Well, let me draw it better. If you go past the North Pole on a geodesic, it would have been better to start on a completely different point on the equator and go the other way around. So when you continue an orthogonal geodesic from the equator past the North Pole, it will stop being length minimizing. The issue is the same as it was before. The orthogonal geodesics from the equator focus at the North Pole, and when continued past a focal point, geodesics stop being length minimizing. It's just that the notion of a focal point is different, slightly different. A focal point corresponds to this picture, that there's some other nearby orthogonal geodesic that meets at the same point, R, let's say. R is the focal point if gamma and gamma prime meet at R. And the idea is the same as before. If you can displace gamma infinitesimally to gamma prime, that will mean that the part of gamma prime up to R has the same length as the part of gamma up to R. That's because orthogonal geodesics extremize the length. So if you have a family of orthogonal geodesics, they have the same length. And again, then by rounding off the kink at R, you can do better. So when you continue past the focal point, you can shorten the length by switching to a different starting point, taking that up to the focal point, and then continuing past the focal point as before. Sorry, that would leave the length unchanged. But then by rounding out the kink, you would reduce the length. I hope I've managed to explain that geometrical picture fairly clearly. Any questions about it?
I do have a question. Would an open disk in R3 be an example of a codimension 1 submanifold? And if so, what if the point was sort of to the side?
Well, let's discuss that example in a moment. Okay. Some further remarks I made here are also applicable. We didn't need to know that all nearby orthogonal geodesics converge at R. We just need to know that there's one that does. And it doesn't have to converge exactly at R. We just need to know that the geodesic, first order equation, the linearized equation, for a displacement of the starting point of the orthogonal geodesic with boundary condition that it should end at R has a solution. So we need to know that this picture exists to first order in epsilon. Then, as before, we lose epsilon cubed in the length by displacing the starting point, but we gain epsilon squared by rounding out the kink. I felt the question was whether W has to be compact. And since the considerations were local along W, the answer is no.
So, if it's an open disk and you're off to the side, what would a geodesic look like that minimizes length? In other words, if you're sort of parallel to the disk.
I'm not promising it exists.
I see. Okay. In that case, yeah. Maybe it exists.
We didn't discuss existence proofs. What we discussed was a necessary condition for an orthogonal geodesic to be length minimizing.
Thanks.
Question.
Yes?
Why do we need orthogonality in the definition?
A geodesic that's not orthogonal is never length minimizing, as you probably learned in high school.
Yeah.
So, right, if you want to go from the y-axis, for example, to a point, the length minimizing geodesic will be orthogonal to the y-axis.
Yeah, so basically we just make it more explicit in the definition.
Well, I wouldn't call it the definition. The very first thing I said was that the condition for a curve from a hypersurface to a point to be an extremum of length is that it's an orthogonal geodesic. That's where you should have asked the question about orthogonality. How did I know that? Assuming we know that, the rest of what I said follows. The way we know that is by literally writing down the formula for the length, and then we extremize it. We have we deduce the Cauchy-Riemann equation, but we also find a boundary condition that we need in order that a surface term in the variation of the length vanishes. And that surface term is orthogonality, as I believe you learned in high school, at least for the case of flat hypersurfaces in Rn, or in some generality. Yeah, I'm not sure in what generality, but in some generality you learned that in high school, I believe. Any other questions? No takers? I think we're finished. Unfortunately, I closed this notebook. I think we're finished with Euclidean signature for the moment. So we can go back to Lorentz signature in the last 5 minutes. I'll say 5 minutes about Lorentz signature, but it's sufficiently important that we'll probably recapitulate it on Tuesday. So we want a Lorentz signature analog. There's none for space-like curves. For example, if you have a space-like curve connecting 2 points, you could make its length be arbitrarily big by making it wiggle in spatial directions. But you could also make its length arbitrarily close to 0 by making it almost light-like. If you go forwards in an almost light-like direction and then go backwards in an almost light-like direction, you can get from Q to P with almost 0 length. On the other hand, if you do it by wiggling, you can make the length arbitrarily big. So there's no useful analog for a space-like curve. However, there are analogs for time-like and light-like and null curves. There's a time-like analog, and there's a more subtle analog for causal curves. Roughly, the time-like analog leads to Hawking's theorem, and the causal analog leads to Penrose's theorem. And it's because the time-like analog is easier to get intuition about that we're going to start with Hawking's theorem. So we've already learned, something, an elementary fact that we've already discussed on Tuesday is that it's possible for a curve to maximize the proper time. So a time-like curve can maximize the proper time. And it turns out that everything we've said about minimizing the length in Euclidean signature has an analog for maximizing the proper time in Lorentz signature. It's sufficiently important that I want to go over it slowly, even though it will involve some slightly repetitious sounding statements. So I'll postpone some things to Tuesday. Maybe one thing I can say now is to give examples of time-like curves that don't maximize the proper time. So, one example is in this space-time. There are many time-like curves, there are many time-like geodesics even, that we get from Q to P. And they can't all maximize the proper time. So most of them don't maximize the proper time, if P is sufficiently far in the future. Another example is in anti-de Sitter 2 space. And we discussed ADS2 last time. So remember the metric is an infinite strip with a factor that blows up when sigma is 0 or pi. And then we considered a point Q, and we considered null rays from Q that reach. We have this nice picture. And one thing which we did with the picture was to observe that if a point P prime is such that from Q a causal curve could get to the boundary on its way to P prime, then there was no upper bound on the proper time elapsed from Q to P prime. But there's actually no geodesic from Q to P prime. So that example doesn't illustrate. I want to give an example of a time-like geodesic that doesn't maximize the proper time. To do that, I have to consider a time-like geodesic from Q. A typical one does this. It goes through the upper point of that diamond and then continues. And now you see we have, so the geodesic I've drawn is just in the middle of the diagram. So the curve sigma equals pi over 2, the middle of the diagram, is a geodesic for this metric. And if you can see that if you can continue that geodesic long enough, you get to a point P double prime that you could have reached. Well, okay. There are focal points. The geodesics from Q all focus at this point. P sub f is for a focal point. The symmetry of de Sitter space, the symmetries of anti-de Sitter space, somewhat like the sphere, but now in Lorentz signature and with negative cosmological constant. Because of the high symmetry of anti-de Sitter space, the geodesics have special properties. They all focus at this point P sub f. And so the point P double prime is past a focal point, and therefore the geodesic can't be maximizing the proper time. That I will explain Tuesday. Sorry. Here I'm just giving an example of a geodesic that doesn't maximize the proper time. It doesn't because we could get longer proper time by going to infinity and back. So from the picture you can see that that geodesic doesn't maximize the proper time. But the relation of that to a focal point will be our first topic Tuesday. And I'm going to conclude by giving one more example, which is a fun example due to Penrose. So we consider the Earth moving around the Sun. So the Earth is moving around the Sun on a time-like geodesic. So like any time-like geodesic, a small portion of it maximizes the proper time. But now look at the Earth moving around the Sun for 1 million years. Launch a rocket from the Earth with almost the escape velocity of the solar system. It goes way, way out. But it doesn't quite have the escape velocity, so after 1 million years it falls back to Earth. It spends almost all of the 1 million years very far from the Sun and with very small velocity. So both the relativistic time dilation and the Lorentz, both the gravitational redshift and the relativistic time dilation affect the spaceship less than they affect the Earth. So the proper time elapsed for the spaceship is bigger than it was for somebody who stayed on Earth. So the orbit of the Earth over 1 million years is not proper time maximizing. That's a fine example that you can find in a relatively little known book by Penrose, which I like much better than the much more famous Hawking-Ellis book, but that's just a personal opinion. So I'll see you Tuesday. Yes.
I think a more basic example would be like if I throw a ball at you, there are two paths, right? Like it follows a parabola, right? And the one above will have a bigger proper time, right? In general. This is even.